part, but we'll focus. So the goal today is to actually finish off submodular optimization. Okay. So today, as we discussed last time, we'll be looking at submodular function optimization. So that's minimization and maximization, right? So this is a picture that we spoke about, in the beginning as well, that we have continuous optimization and we have discrete optimization. So the two are related because you take a kind of discrete optimization problem and you relax it and you get a continuous optimization problem, right? And then you further do a rounding to get a discrete problem. So we'll actually study this loop when we talk about submodular minimization. And as I said, a lot of these state-of-the-art algorithms today for submodular minimization, in fact, use this relaxation using the Lovasz extension. All right, so this is just some acknowledgements that a lot of this is borrowed from Jeff's kind of lecture notes from UW, some tutorials at NIPS, ICML, etc., and some of my tutorials. And this is some reading material, that is interesting. There's Francis Bock's monograph on submodular minimization and convexity. Andreas Krauser has kind of a nice book. Also, it's kind of linked on the course webpage on submodular maximization. Okay, and this is just some links of the same things. So submodularity has this kind of convex aspect and it has the concave aspect, right? So convex aspect is useful for minimization, concave aspect is useful for maximization, and it has aspects that are related to neither, right? So it's kind of related to convexity, is related to concavity, and like it has certain kind of peculiar things that is neither convex nor concave. So it's definitely not the same as convexity and concavity, but it's like analogous to both of these. And this kind of weird analogy makes it amenable to actually both minimization and maximization. So that's kind of typically not the case when you look at continuous optimization, because if something is easy to minimize, like a convex function, if it can be minimized, then it's not it's kind of NP hard to maximize, right? Or it's in fact not even approximable to maximize a convex function. Whereas submodular functions can be, reasonably well, it can be minimized and maximized, in fact, under like multiple constraints. And we'll also talk about kind of approximation algorithms and what approximation guarantees mean over here, and we'll study some of this here. Okay. So this is some kind of relationship between submodularity, convexity, and concavity. There's in fact many papers that talk about this. In fact, we have some papers. I have a 2015 paper called Polyhedral Aspects of Submodularity, Convexity, and Concavity, and we have a 2020 paper called The Concave Aspects of Submodular Functions in ISIT. But the high-level intuition here is that the convex aspects allow for minimization, right? The convex aspects allow for a nice kind of convex continuous extension called a Lovasz extension, which is piecewise smooth. It allows for subgradients and subdifferentials, and it allows for a nice convex duality, discrete separation results, so on and so forth, right? The concave aspects actually allow for maximization, right? So essentially, convex functions can be minimized easily, right? But concave functions can be maximized easily, right? So kind of taking the analogy from concavity, submodular functions can be maximized, but not as easily as they can be minimized, right? So they are kind of NP hard to maximize, but you can achieve constant factor approximation guarantees. And we'll exactly talk about what we mean by constant factor approximation. So it's kind of okay if you don't understand that completely, but just at a high level right now, right? Then we have the multilinear extension, right? So the multilinear extension is concave in a direction, right? And again, I'll talk about what the multilinear extension is, but it has some properties related to concavity, right? Just like you can define subgradients and subdifferentials. So in some of the early classes of convex analysis and convex functions, we spoke about the subdifferentials and the subgradients, and the concave aspects have kind of analogous supergradients and superdifferentials. Okay. And finally, you have like convex duality and discrete separation kind of theorems. you have similar results in the concave aspects. Under certain restrictions, you have a duality result and a discrete separation result. Um, okay, any questions on this right now? Okay. So to understand this a little better, we will be using this kind of analogy to go between between subsets and between vectors, right? So essentially, you have a set A, which is say A comma B, right? And we have a set function f going from 2 raised to b to r. Oh, so actually, there's a question. Yeah, so basically, Parth, what happened is that last time this particular lecture I forgot to record it, so there's no record. Unfortunately, there's no record of this lecture, so that's why I'm kind of going over this again. So part of it can be recorded. So I'm really sorry about this. Apologies. Yeah, I mean it's kind of unfortunate. The second part I forgot to probably record it, so that's what happened. But anyways, let me know if you have any questions or if anything is unclear, right? So the basic notation here is that you have a set, right? So in this case, A comma B is a subset, right? So imagine that your ground set here V, right, is A comma B comma C comma D, right? So if B is A B C D, then your subset A is here A comma B, right? So this is your subset, and your the kind of analogy here is to create a function capital F and view it as a Boolean function. Okay, so what we mean by or actually it's also called a pseudo Boolean function. So by the way, Boolean functions, strictly speaking, are functions that are defined from like say 0, 1 raised to n, right? And they output something between 0, 1, right? So the output of a Boolean function also is a bool. So it's like 0 to 1, right? Whereas in our case, the functions don't output Boolean values, they output like real numbers, right? So that's why this function is actually called a pseudo Boolean function, right? So pseudo Boolean function means that it kind of takes in Boolean arguments, right? So the vector x is a Boolean vector, but it takes in it actually outputs again a real number. Yeah, and actually like there's a lot of work on this by Hammer, as Professor Chandrasekharan has kind of pointed out. So in fact, I think he has a nice it's Hammer and someone else. I can't remember this paper. He has actually a book where he talks extensively on pseudo Boolean functions, and he talks about like the submodularity, like under what conditions are pseudo Boolean functions submodular, supermodular, and he talks about like some of these higher order, kind of higher order submodularity properties and so on and so forth. So it's actually a nice book. But yeah, so the and kind of this analogy will be useful for us to understand the kind of minimization variant here, right? Because you can kind of translate now your set A into a X, right? And X here is EA, which is an indicator on the set A, right? So basically what this means is that it is 1 on the elements which are in A, right? So for example, here A and B have a value 1, whereas C and D are actually 0, right? So both of these are equivalent. So this is what we kind of discussed last time, right? Then we spoke about continuous extensions. So essentially, we have a kind of the kind of pseudo Boolean function, right? That is defined on 0, 1. So it's kind of not defined on the points in between. It is only defined on the extreme points of this hypercube, right? And on kind of every extreme point, you have kind of values which are real numbers, and this is pseudo Boolean function. So this is a discrete function. And then we have a continuous extension. So you can have a concave extension. So a concave extension is an extension. So basically by default, since it's an extension, it needs to match on the extreme points of this hypercube, right? So we needed to exactly match this pseudo Boolean function, but everywhere else it can have any other value, right? So such an extension is called a concave extension if the function is concave, right? And it extends the submodular function, right? So the basic intuition here is that now we are kind of transforming this discrete problem into a continuous problem, and hopefully we can optimize this. Yes, Professor. Professor, I think we can't hear you actually.
I'm sorry. Is it always possible to take a function that is defined on 0, 1 vectors and extend it to a concave function?
Yes.
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 I'm not
Yeah.
so
So it is
sure.
actually.
Don't we need discrete concavity or discrete convexity before we extend?
No. So for the result, so actually there is a result which in fact we also showed in our 2000. So we have so I have a 2015 paper called Polyhedral Aspects of Submodularity, Convexity, and Concavity. So building up upon some previous work, what we showed over there is that you can actually mathematically define an extension that is convex or concave, right? The trick, the kind of tricky part comes that you cannot, so it's not always that it's easy to compute, right?
You started with a submodular function. I was thinking about any function defined on 0, 1 vector.
Right. So actually, this can be defined for any function, actually, Professor. So you're right that for a submodular function, also the concave extension turns out to be not easy to compute, just the way the convex extension is not easy to compute. But in fact, you can kind of extend this now because since any function can be decomposed into like a convex minus. So essentially, like one simple way to view this, right? You have any set function h, right? This is like any set function. You can write this as a difference between f minus g, right? Where f and g are both submodular. So now what you can do is you can look at, say, a concave extension of f and a convex extension of g, right? And then you will get basically a function that is actually kind of concave, right? Because it's concave minus convex. And this would be an extension. So I mean, like vice versa, you can do convex of f and concave of g, right? And then you get a convex extension. So you can get both convex and concave extensions, but the precise problem is twofold. One is that for any set function, computing this f minus g may not be obtainable in polynomial time, though there exists a f and g, right? It's not the case that you can easily compute this. And the second problem is that even if you can compute this, computing the concave extension of a submodular function is actually not easy.
Thank you. Very interesting.
Yeah. So this is actually kind of mathematically an interesting kind of side point. But it turns out that the convex extension of a submodular function, thanks to this result of Lovasz, can be computed easily. And there are certain subclasses of concave functions where the concave extension can in fact be computed. So there's been some work in the CS theory community where they have shown that these are related to like matroid rank functions. And for those functions, you can actually compute the concave extension efficiently. Yeah. But thank you. This is a great question, actually. Um, so, so basically, what we discussed last time is that the concave extension may or may not be differentiable, right? So this is an example of a concave extension which is continuous, right, but non-differentiable, and this is an example of a differentiable concave extension, right? This is an extension which is linear, right? So it's kind of both concave and convex, but basically, as you can imagine, linear extensions can only be computed if the function inherently is kind of additive, right? So basically, if it's a modular function, so only modular functions will give you linear, right? So only modular functions will give you linear extensions. Arbitrary functions may not kind of give you linear extensions, right? And you can similarly have a convex extension here, and the convex extension is again basically an extension of a function which is convex, right? So again, you can have a differentiable convex extension or continuous but non-differentiable convex extension. So the Lovasz extension that we again spoke about last time falls here, right? So this is the Lovasz extension. So any questions on this so far? Okay. So again, we kind of spent some time talking about this, so I'll just go over this, just to kind of recap, because it's slightly more involved. So maybe I'll just erase some of these points because this is not super critical. But we spoke about a polyhedra, a kind of polyhedra. We spoke about polyhedra last time, right? So polyhedron is basically a set of points that can be defined via a subset of linear inequalities, right? Now, the submodular polyhedron is a function, or actually is a polyhedron that can be defined via a possibly exponential number of inequalities defined using a submodular function, right? So essentially, what this polyhedron says is that it's a set of all x in R raised to n, such that for every subset A, right? So this is now I'm looking at 2 raised to size of v, right, which is equal to 2 raised to n, assuming like size of v is equal to n, right? So I'm looking at 2 raised to n number of inequalities, right? And amongst all of these 2 raised to n number of inequalities, I want that this basically this inequalities must be true, right? So x of a must be less than equal to f of a, right? And x of a here is actually equal to the sum of I in a xi, right? So this is additive function on x, right? And we want that this should be kind of lower bounded by f of a for every subset a. So f is a function given to you. Imagine you can enumerate this 2 raised to n times, right? And when you enumerate this 2 raised to n times, you get this inequality, right? So basically, I took this example over here that imagine this is like 2-dimensional case, right? So you have a and b. Then you have basically xb is less than or equal to f of b, right? And you have like x of a is less than equal to f of a. So this is just looking at the singletons, right? And finally, you have x of a plus x of b plus x of b is actually less than equal to f of a comma b, right? So because of submodularity, you know that f of a comma b is actually less than fa plus fb, right? So that's why this is, in some sense, this point is so that's the reason why you will see that this line that I'm drawing, this line which is like the f, this inequality will always exist, right? So this is not so it's not the case that this inequality, these two inequalities get rid of this inequality, right? You see what I'm saying? Because f of a comma b is actually less than the sum of this, right? This inequality is still active. So in fact, all three of these inequalities are actually active for a submodular function. Okay. So essentially, this region that I've drawn here, so maybe I'll just change the color. But basically, what I'm trying to say is that yeah, maybe I'll just continue with this color. But basically, this region, right? So this entire region is kind of the PF, right? And this region is the submodular polyhedron. So essentially, this region over here, right? And kind of it goes so these lines that I'm kind of showing are the extreme faces of this submodular polyhedron. Okay, is this clear to everyone? So you have these three inequalities. This is how you would get the submodular polyhedron. And yes, Professor.
Your submodular polyhedron may have extreme rays.
Mm-hmm. Yes.
Thank you.
Yeah. And this is how so this is the shape of the polyhedron, like that we spoke about last time. And kind of depending on how the function looks like, you have different. So like this could come, for example, in the top quadrant, or it could come down. But basically the point is that you have this structure essentially, right? So now using this submodular polyhedron, so is the domain of f real? Yeah, the domain of f is real. Yes. Yes. Okay. So the convex extension now, right, is essentially so the convex extension will actually use So is V a set? Yes, V is a set. So V is the ground set, right? So this is what we spoke about last time as well. So V is the universe of all possible items, and I'm selecting a subset A from V. Is this clear? So, yeah. Okay. Stop me, by the way, if you have any questions, because it's somewhat important to understand this, the kind of math going on here, right? So, all right. So now we'll use the submodular polyhedron, and using the submodular polyhedron, we can compute these kind of interesting extensions, right? So, one such interesting extension is the Lovasz extension of the submodular function, and this was um, kind of shown by Lovasz in 1982, 83. But actually before that, in 1981, it was shown that submodular minimization is actually polynomial time, right? And the way they showed this at that time was not necessarily using the Lovasz extension, but using a kind of ellipsoidal approximation based, I mean, sorry, not approximation, and kind of ellipsoidal algorithm to do submodular minimization, but that was not really a kind of practical algorithm, right? But at least for the first time, it showed that submodular minimization is polynomial time. And then in 1982, 83, this interesting extension called the Lovasz extension was shown by Lovasz, right? And the idea here is that you take the submodular polyhedron, right? So note, by the way, over here that this polyhedron can be defined on any submodular function, or no, sorry, any set function. It's not necessarily submodular, right? So that's the critical thing. You can define a submodular function on any set function, and you can actually probably come up with an extension like this, which is kind of convex function, right? So the basic idea, so Professor Chandrasekharan, to answer your question, right? The basic idea here of the proof that will show that a convex or a concave extension can be computed for any set function is to actually come up with a polyhedron like this defined on any set function, right? So there is one caveat. I'll not get into that very, I mean, because it's a little bit more involved, but it turns out that this polyhedron is very special, right? The reason why it's very special is because you just have x of a. You don't need any additional b. Okay. So again, this is just some bonus slides, just just in the interest of the questions that Professor Chandrasekharan brought up, right? But I'll just talk about it. Yes.
I think you are lucky that the original thing was only on 0, 1 to the n, not on
Yes.
integer vectors. I was thinking of integer vectors. Function defined on integer vectors can be extended to the reals in a convex fashion. That is not always possible. That is where I was.
Yes. That's a good point. Yes. Yes. Thank you. But there's this interesting connection that I'll talk about. So we talk about this in our 2015 paper called Polyhedral Aspects of Submodularity, Convexity, and Concavity. Right. So we define, so basically you can kind of write down P of F as X such that X of A is less than equal to F of A for all subsets A, right? It turns out that this can be defined for a submodular function, right? But now the question is that can we define this for any arbitrary function, right? So the question is, can we compute F tilde of X to be equal to max of Y in P of F of X transpose Y, right? So does this work any set function? So it turns out that there is a catch over here, and mainly the catch is that this polyhedron, right, turns out to be not very interesting in the more general case. So in fact, this function may not actually be an extension for any arbitrary set function, right? But it turns out you can actually fix this easily. So you can define a p hat f to be the set of X such that X of A plus B. So this is actually it's actually a polyhedron in, so it's x comma b in r raised to n plus 1, right? Such that x of a plus b is less than equal to f of a, right? So we add one more dimension, which is a bias term, right? And you're adding a bias term, and you want to have this less than equal to f of a, right? So this is different from this. It turns out that, oh sorry. So it turns out that if f is submodular, right, then you can show that max of y in pf of x transpose y is exactly the same as max of y in pf tilde of x transpose y, right? So in some sense, this guy over here, the p hat f, is the set of all possible like modular upper bounds which also have a bias, right? So it's in some sense the affine variant over here, that you have these affine functions and you have these functions lower bounding f of a, right? So actually, I'm sorry. I think this should be y comma b belonging to p hat of f of x transpose y plus b. Okay. So it turns out that if f is submodular, both of these are the same, right? And for any arbitrary set function f, right, you can define f tilde of x to be basically this max of y comma b in p hat f of x transpose y plus b, and this is convex. But the problem, as as you can expect, the problem is that it's not always easy to compute this. Okay, so that's where the catch is. So even though you can compute a convex extension, you can't necessarily compute this max in polynomial time. Whereas thanks to the Lovasz extension and this algorithm, which we'll talk about next, we can actually do this. This max can be done easily if it's a submodular function. Okay, so this is a slight detour, just to kind of, yeah, Nathan.
So just to be sure, if you want a convex extension for any set function, you need to use this max over this this new polyhedron of x transpose y plus b, not only x transpose y.
Yes, that's right. That's right. So if f is an arbitrary set function, so in fact, you can do this for a supermodular function, right? And it turns out that for a supermodular function, if you just do this, it is actually kind of almost meaningless, right? And the reason why that's the case is because if f is supermodular, right, then f of a comma b is actually larger than f of a plus f of b, right? And because it is larger than f of a plus f of b, this inequality is meaningless. It in fact gets thrown out, right? So in 2 dimension, the supermodular polyhedron will actually look like this. It's going to be, it's not going to be an interesting polyhedron like the way it is for the submodular case. It's actually like just a kind of, this is in 2 dimension, but you can kind of extend this to n dimensions as well, right? And you can see that it just has one single extreme point. The supermodular polyhedron just has one single extreme point, and that is this set of f of a, I mean basically f of I for all I in B, right? So it has one single extreme point, and you can compute the max, but that max is not very interesting. It's not going to give you an extension of the supermodular function. So that's the reason why you need to do this, and this is the correct extension. This is the correct extension in the general set function case. Okay. So anyways, this was just a detour, just to kind of give you a perspective, right, of what's going on. All right, but now I think we can talk about the Lovasz extension. Okay, so Lovasz extension is this kind of nice quantity here, which is max of y in P of f of x transpose y. This is attributed to Lovasz, that's why his name comes in. In fact, Lovasz actually won the Abel Prize, I think, this year, which is a kind of actually I can't remember, but I think he kind of won a very important Prize from the kind of mathematics community, even though he's from the kind of CS, the theoretical CS/math community. He's done a lot. He's actually done a lot of similar work in multiple areas. One such area is submodular optimization, and he has this nice work on this relationship between convex optimization and submodular optimization. Okay, so now thanks to this, what it turns out that we will actually talk about now is that we can exactly do submodular minimization, right, by relaxing this to the continuous domain and solving the convex minimization, right? So doing minimum over x in 0, 1 raised to n of f of x, and both of these are exactly identical, right? So what I mean by both of these being identical is that you can actually minimize the left-hand side, right, which is the convex minimization. You can achieve a continuous value x, and you can actually relax this x to a discrete set, capital X, right, without losing any information. Yeah. So thank you, Nathan. Yeah. So actually, Lovasz won the Abel Prize this year. So basically the algorithm, right? So the kind of simplest algorithm, or actually maybe I'll call it the minimizing submodular functions using the Lovasz extension. Okay, so I've not yet told you how you can compute the Lovasz extension. We'll actually talk about that in the next slide. But the first step is, okay, so basically we are given a ground set V and a submodular function f defined from 2 raised to v to r, right? So we are given these two, and the output of this algorithm is a subset x of v, right? So basically there are just two steps over here. So the first is compute the Lovasz extension. We'll talk about this in the next slide. So what we exactly mean by what is the Lovasz extension? How will we compute this, right? Then minimize x belonging to r raised to n, or actually it's not x in r raised to n, it is actually x in 0, 1 raised to n. Okay? So I'm relaxing this to be, so this is a constraint optimization, and like we saw that constraint optimization is possible, right? But this is a very easy constraint. We can solve this using projected gradient descent as an example, right? I mean, there are multiple other ways of solving this, but as an example, we can actually minimize this using a projected gradient descent, right? So you have the Lovasz extension here. This is convex. It is easy to minimize. It is not differentiable, right? But it is still continuous and convex, right? So in order 1 over epsilon square, we actually saw this. We can minimize this up to approximation guarantee of epsilon, right? Up to an additive factor of epsilon, right? Any questions on this so far? So we will just use projected gradient descent here, right? Okay. So the third step is that once we achieve this x, yes, Nathan.
Yeah, so I just want to be clear. Where did we see the order 1 over epsilon squared convergence?
Oh, so this is the convergence for basically for Lipschitz continuous functions, right?
Using just regular, well, using projected gradient descent.
Exactly. So you just do Lipschitz continuous functions. We saw that without any projection, just in the standard case, this has order 1 over epsilon square, and we also saw that if you add an additional projection step, it does not change the analysis. I mean, it doesn't change the result. Just the analysis changes very slightly to add the projection. But as long as the projection can be computed easily, we can do this in the same. So the only constraint here is that projection needs to be computed easily, right? And it turns out that the projection can be computed easily here because this is just x in 0, 1 ratio n, right? So it's basically the constraints over here is just that xi is between 0 and 1. So it's a box constraint, right? And it turns out that the Lovasz extension is Lipschitz continuous. So all of that machinery goes through, right? So once we achieve a x star, right? So once we obtain x hat from step 2, right? We can round x hat to obtain the set capital X hat, right? And I'll talk about the rounding algorithm also next, but this is the basic procedure, right? So the question then is that, what is this step, right? This step is clear, right? We will use an existing algorithm we saw in the first part of the course. And the third step is how do we round this to obtain an X hat, right? So we'll actually talk about all of this now, but I just wanted to give you the high level flavor, right? So we spoke about this last time towards the end, but I'll just kind of recap this again. So the question is, how do we evaluate the Lovasz extension, right? How do we compute the Lovasz extension? So recall that P of F is a submodular polyhedron, and this is the set of all A subset of V such that X of A is less than or equal to F of A for all subsets A, right? And the Lovasz extension requires exponentially many constraints, but it turns out that this can actually be computed in order n log n time, right? So this was actually shown in by Edmonds in 1970, right? That that even though the submodular polyhedron has exponential number of constraints in it, you can actually compute this maximization over the polyhedron. So basically, you can solve a linear program over this polyhedron in n log n time, right? And the idea here is that we take a greedy algorithm, right, and we sort x. So the way we sort x is that we obtain a permutation sigma 1, sigma 2 until sigma n, such that x of sigma 1, right, is greater than or equal to x of sigma 2, and in turn is greater than or equal to x of sigma n, right? And once we compute this ordering, then we define y hat x of sigma I, right? So the sigma ith coordinate of y hat x to be f of sigma I minus f of sigma I minus 1, right? Sorry, not sigma I, this is s actually. So somehow this looks like delta. So I think I really need to improve my handwriting. Right, so this is s of I minus s of I minus 1, right? So s of I over here is equal to this chain of sets, right? So s of I is equal to sigma 1 to sigma I, okay? And once you compute this y hat of x is a vector. Once you compute y hat of x, the Lovasz extension is nothing but x transpose y hat of x, right? So it's a very simple n log n algorithm where for a given x you can compute the Lovasz extension in roughly order n log n. Any questions on this? So we saw this example last time. So take x to be 0.1, 0.4, 0.2, 0.05, 0.9. So this is a real vector, right? Vector in r raised to 5. So the sigma over here, once you sort this, is the highest value is 5, 2, right, comma 3, 1, 4, right? So this is going to be the ordering now. And once you have this ordering, then you use this ordering to compute this quantity, right? So we spent some time with some intuition to understand what the Lovasz extension is, and the takeaway was that essentially this is a piecewise linear function that looks something like this, right? And this change that happens, this point in like the two-dimensional case where you have 2 dimensions, where you have a ground state of size 2 basically, right? That this change will happen along a line, right? And this line is nothing but the line of x1 equal to x2. So for the part where x1 is greater than or equal to x2, right, this part, you have essentially the ordering as follows, right? So you have the ordering as 1, 2, and then you compute this y vector to be y1 equal to f1 minus f of the empty set, and y2 to be f of 1 comma 2 minus f of 1, right? And then you get this vector y, which is y1 y2, and then the Lovasz extension here is linear. It is exactly y transpose x. Y is a fixed vector, right? So this is fixed. It's a fixed vector, so that's why it's exactly a linear function. But it's a linear function only in this region. Okay. Once I come to the top region, I have x1 less than equal to x2 over here, right? And since x1 is less than equal to x2, I define a new vector z such that z2 is defined as f of 2 minus f of the empty set, and z1 is defined as f of 1 comma 2 minus f of 2, right? And this guy now, f of x over here, is actually a different linear function, which is z transpose x, but both of these match at this line, which is x1 equal to x2. So this is a Lovasz extension, right? So Lovasz extension looks like this. So it's linear over here and it's linear on this side. Okay, so it's basically like a V shaped in 2 dimensions. Okay, so you can imagine that it's a V shaped going down in 2 dimensions. Does that answer your question? I mean, like, is this clear to everyone? The intuition of the Lovasz extension in 2D, and the same intuition basically carries over in n dimension as well. Yes, Nathan.
So is that V you drew at the bottom right like the image of the function whenever you consider a point in r squared, or?
Yeah, so this is, I mean, this is just an illustration. Actually, in if you have a 2-dimensional thing, right, then you'll have something like this. So in 2 dimensions, this is your x1, this is your x2, right, and then your 3rd dimension over here is your y, right, which is basically f of x1 comma x2, right? And essentially, this is the line in which the function will change. So essentially, in this part, right, in this part, you have one slope, right, and in this part, right, you have another slope, basically.
Okay.
Does it make sense? So maybe ignore this drawing, but really, this is how the function looks like, and like it's because more complicated in the 3 dimension. Unfortunately, in 1 dimension, the Lovasz extension doesn't really make sense, right? Because there is no ordering. You just have one quantity. So in 1 dimension, it's just going to be a linear function. That's it. There's nothing interesting in the Lovasz extension. It becomes interesting in like greater than 1 dimension. So that's the reason why the Lovasz extension actually I think the number of pieces is what the question is about in n dimension. Yeah, so in n dimension, you basically for every permutation, right? So essentially, the way this works is that you can take every possible permutation of x1 to xn, right? And for every possible permutation, you have your Lovasz extension, right? So the Lovasz extension differs depending on the number of ordering. So you have n factorial. So in n dimension, you have n factorial number of orderings, right? So for each of these orderings, you have a different kind of value. I mean, you have a different y sigma. So that's the reason why essentially the best way to think of the Lovasz extension is exactly x transpose y of sigma x. So y does not depend on x, it depends on sigma x. So as long as 2 values of y, right? So basically 2 y's. Well, actually, sorry. Yeah. So essentially 2 x's, right? 2 x's that have the same ordering will have exactly the same linear function. Does it make sense? So the Lovasz extension, the slope of the Lovasz extension, right, or this y, just depends on the ordering induced by x, nothing else. Doesn't depend on x itself. So that's the reason there is actually an interesting kind of connection here to look at a class of distance functions defined by the Lovasz extension. And it turns out that you can actually compute a distance function called the Lovasz-Bregman divergence, right? And it's kind of a Bregman divergence, but it turns out that this is very interesting because you can now define distance functions between x's and a permutation, right? And you can do this for like all kinds of interesting applications, like ranking functions, like ranking kind of applications, right? So like where you want to learn to rank, for example. So actually there are a number of interesting things that can be potentially done on this Lovasz extension thing. And I think the main reason for this is because the Lovasz extension inherently depends on the ordering induced by X, right? So, all right. Any other questions on this right now? Okay, so we spoke about the properties. I'll kind of very quickly go over these right now. So you have the Lovasz extension operator, and the Lovasz extension is basically additive. So the Lovasz extension of f plus g is nothing but f tilde plus g tilde. The Lovasz extension of lambda times f is nothing but lambda times f tilde, right? The Lovasz extension has this nice property of positive homogeneity. So the Lovasz extension of alpha times w is alpha times Lovasz extension of w. The Lovasz extension of the indicator of a set is nothing but f of a, so it matches at the vertices of the hypercube, and so on and so forth. Right? So we have several interesting properties. You can go over these offline. There is also some examples of the Lovasz extension. So we are assuming over here that the w is positive, right? So the w vector is positive. Then the Lovasz extension of the cardinality function is the one norm of w. The Lovasz extension of the minimum of size of a comma 1 is the infinity norm of w, and so on and so forth, right? So you have like multiple other interesting kind of definitions of the Lovasz extension as well, right? All right. So now we will switch gears a little bit, right? So I think you understand the Lovasz extension. I will come back to this algorithm, by the way. So just remind me. I'll come back to this algorithm because we'll talk about submodular minimization soon. So that time I'll talk about the rounding scheme, etc. But before that, I'll talk about the submodular semi-gradients, right? So the subgradients are essentially so recall from convex analysis, right? That given a convex function phi, you can come up with a subgradient, right? And a subgradient is nothing but this particular quantity, right? Which in this case is exactly the gradient, but you can actually write this as a subgradient as well, because you can have that, you know, it's not exactly differentiable, right? So in that case, you will have phi of y is greater than or equal to phi of x plus hx of y minus x, right? So this is h phi of x. So this is nothing but the subgradient over here, right? And so this is phi actually, okay? So this function now can be computed for any convex function, even if it's not differentiable. Similarly, for any concave function, you can come up with a super gradient, right? So you have like psi of y is less than or equal to psi of x plus h x psi of y minus x, right? Or maybe I'll call this g because I'm using the notation g down. Okay? So we'll call this gx of psi, right? And now h is a subgradient, g is a supergradient, right? But you can come up with these subgradients and supergradients for convex functions, right? So the question is, can we do something similar for submodular functions? Okay, so it turns out that you can define a subgradient of a submodular function, and the subgradient, I'll actually add a f here just to be clear that this is the subgradient of f, right? So a subgradient is exactly a vector hf of x which satisfies this for every subset y, right? So for every subset y, you have f of y is greater than or equal to f of x plus hxf of y minus hxf of x. Okay. You can do the same for the other case as well. So you have the upper bounds of the submodular function, and these upper bounds can be obtained by using supergradients of a submodular function. Okay, now the interesting question is, can we first of all compute these subgradients and supergradients, and secondly, do there exist subgradients and supergradients everywhere, right? So we know for a convex function that you can only compute a subgradient. You can't compute a supergradient of a convex function, right? Because you can't, I mean, there is really no upper bound of a convex function that can be computed everywhere, right? Similarly, there is no kind of lower bound that can be computed for a concave function. So for a continuous function, you only have convex extensions. I'm sorry, you only have kind of linear lower bounds, and for concave functions, you only have linear upper bounds. But it turns out that for a submodular function, you can actually do both. In fact, this is related to a point that what was asked earlier by Professor Chandrasekharan, because you can actually compute, in theory, you can compute a convex and a concave extension of a submodular function, right? So that's the reason why for a submodular function you can actually compute a convex and a linear lower bound and a linear upper bound. So we can actually define both subgradients and supergradients for a submodular function. So this is the intuition. And the way you compute a semi-gradient actually was shown by Fujishige in 2015. And the idea is that you can actually compute the subgradient in a very similar way to the way we do it in the Lovasz extension, right? The only difference now is that given a set Y, the way we do it is that you can okay, so there's a question here that we are computing the Lovasz extension, minimizing x and rounding x, but for computing the Lovasz extension, we need x. Are these two x's different? Okay, so maybe Harsha will actually come back to the minimization, and I'll exactly answer your question at that time. Let us just finish the preliminaries first, and then I'll come back to answer your question. Okay. Sorry. Now the subgradient, right, is defined with respect to a set X. Okay, so the way you define the subgradient is actually very similar to the way you compute the Lovasz extensions and kind of analogously kind of extreme points of the submodular polyhedron, right? So okay, so upfront, I think I should mention this, that for those of you interested from the polyhedral perspective, that the subgradients or the subdifferential of a submodular function also is a polyhedron. Okay, and I will just kind of just point this out very briefly, just for completeness. Even if you don't understand everything, it's fine right now, right? But the polyhedron, right? So given a subset X, this is called a subdifferential. The same can be applied for the superdifferential as well, right? So the subdifferential is the set of all X, right, in R raised to n, right, such that this X satisfies the following, that for every set Y, we actually have f of Y is greater than or equal to f of X plus x of Y minus x of X, right, for all subsets Y in V. So this is now a polyhedron. Okay, so what's going on here? All right, so I'll just explain this at a very, very high level. You are given a subset X and you are trying to compute a subdifferential on the subset X. What does it mean? We want to compute all the subgradients of X such that we can have linear lower bounds or modular lower bounds, right? So over here, X is a given set. You are given the set X. Now, for this given set X, we want to satisfy, so we want this small x to satisfy this inequality. And lo and behold, this is exactly the inequality of what a subgradient should satisfy, right? So it is exactly this inequality, that f of Y is greater than or equal to f of X plus hx of Y minus hx of X, right? So we exactly want this small x to be a subgradient such that f of Y is greater than or equal to this property, right? So what this means is that this term here, right, is actually a modular lower bound of f, which is tight at the set capital X, right? So the reason why is it tight at X, because if I substitute y capital Y equal to capital X, right, then basically we are left with equality over here, right? Because these two terms get cancelled, and then we have like basically f of x is equal to this, right? So this term will exactly be equal to f of x when the set capital X is equal to y. So it's a tight modular lower bound. Everywhere else it is possibly lower than it, but it is tight. So it's exactly this analogy, right? So you have your, I'm drawing a continuous function here because it's just easy to draw it in the continuous space. It's harder to draw it in a discrete space, right? So imagine this is the set capital X. So I have my linear lower bound here. So I'm finding all x's such that it is a linear lower bound everywhere, right? And this x exactly is this polyhedron over here. Is this clear to everyone? How this is a polyhedron? Any questions on this? All right. So now, given that this is a polyhedron, right? An interesting question is, can we compute? So this is a subgradient, subdifferential, right? For a given set X. So can we compute these extreme points, right? Or these vertices of these? So this is exactly how you can compute these vertices. So in fact, to be actually very precise, Fujishige, this is actually all there in Fujishige's book from 2005. But it was shown by Fujishige in 1984. So he has a 1984 paper where he actually kind of showed, gave this result, right? And essentially the result is that you can compute the subgradients, specific subgradients, which is actually extreme points of the subdifferentials, using exactly this algorithm, right? So the idea is that you take your set Y, you're computing the Y at the set. So for now, I'm computing the subgradient at the set Y, right? Okay, so again, sorry, here I did it at the set X, but for now, for this slide, imagine you're computing the subgradient at the set Y. So the way this will work is that you take your set Y and you order the elements within Y and you order the elements outside Y, right? So we need a possible, we need a ordering such that once you order the elements within Y, sigma 1, sigma 2, sigma 3, sigma 4, this should be exactly the set Y. As long as you have such a ordering, which is aware of Y, right? So I'll call this actually sigma Y. You compute your subgradient in the same way that we did for the Lovasz extension, right? You do h y f of sigma yi to be equal to fsi minus fsi minus 1. Okay. So this is the modular lower bound, and you can compute now this nice kind of mathematical term. And you can similarly compute actually, okay, so before going to the supergradients, is the subgradient clear to everyone? That this is an algorithm to actually get specific subgradients. Now, the reason why I'm talking about this, by the way, is we will actually be using the ideas here in the algorithms. So I know it's a little bit more technical and a little bit more mathematical, but just make sure you are following this at least at a high level, right? So that you know we can use this in the algorithms that we talk about, right? Okay, so similarly, we can actually also come up with the supergradients of a submodular function, right? And it turns out that you can actually compute the supergradients easily. So in our 2013 work at ICML, actually a few years back, several years back, maybe 8 years back now, we came up with these supergradients, right? And these supergradients are in fact specific supergradients which allow for modular upper bound. So just the way you have the subdifferentials, right? You can also compute the super differentials. Maybe I'll use another color here. So we can come up with the super differentials. Okay, and the super differentials is exactly the so maybe for simplicity, this is a kind of notational thing that we do here, just to make things clear. So I'll use delta sub f to correspond to the sub gradient here, right? And I'll use deltas, yeah, so this is a sub differential, and I'll use delta sup f of x to correspond to the super differential, right? And this is nothing but the set of all x in r raised to n, such that f of y is actually less than equal to f of x plus x of y minus x of x, right? So this is a super differential of a submodular function, right? And it turns out that we can similarly characterize the super differentials, albeit not in as good a way as the sub differentials can be characterized, but we can still at least compute specific subgradients. Specific subgradients. In fact, in our 2015 paper that I pointed out earlier, we actually try to analyze the super differential. So it turns out that the super differential is actually harder to characterize because computing the extreme points is actually NP hard. Is NP hard, right? But what we could show in that paper is actually we can compute. So I'll just maybe add one more slide here. So imagine that this is the super differential, right? So computing this exactly is actually NP hard to compute extreme points. Even like rays and facets and all of these things, right? These are all kind of harder to characterize. But we can actually come up with a sequence of bounds on these, right? Like kind of lower bounds or inner bounds of this polyhedron, and we can similarly kind of come up with upper bounds of these polyhedra, right? So like this is outer bounds, right? Right until the point where we have this almost trivial outer bound, which is something like this, right? So okay, so maybe let me draw this a little bit more carefully, because it's not exactly like this. In 2 dimensions, the way this would look like would be something like this, right? And then we can come up with some outer bounds which are like something like this, right? Right until we come up with the most extreme outer bound, which looks something to this effect, right? So which is a very simple polyhedron that is like something like a kind of a hypercube, right? Except the hypercube has only one extreme point. So all of these rays go until infinity, right? There's just one extreme point over here. So sorry, I'm being very loose in characterizing this at a high level, but we try to be precise in that paper to exactly understand this. But the high level point is that we have a sequence of inner bounds and we have a sequence of outer bounds, right? So in some sense, the hardness of, so what we argue over there is that the hardness of computing these super differentials is related to the hardness of submodular max. Right? So this is the kind of connection over here, and in fact, since you can approximate the super differentials, you can kind of okay. So maybe I'll point out one more thing, that in the case of submodular minimization, this is also a nice property here. Yes, Professor.
Are the green and the red approximation things computable polynomially? Is that what you're saying?
Yes, exactly. So they are computable. They can be computed polynomially, right? And in fact, they are relatively simple polyhedra that can be obtained using specific supergradients, right? So the green ones can be computed by kind of convex combinations of specific supergradients, and the red one can be computed by relaxing the inequalities, right? So recall that you have 2 raised to n number of inequalities, right? You can relax these inequalities by considering polynomial number of them, right? So for example, you consider only inequalities where the set, so over here you have the set y, right? So you can restrict y to be just like neighbors of x, right? Where y minus x is of size 1. Then you can go to y minus x of size 2, and so on and so forth, right? So by kind of sequentially considering larger and larger differences between y minus x, you get closer and closer bounds to this, right? But the interesting point of why this is useful is as follows. So I'll just connect this one piece over here. So there is a result in submodular minimization that says that x star is a minima of a function, of a submodular function if 0 belongs to the subgradient of x, right? So this is kind of this nice property, which also holds from convexity, by the way, right? So, but this can also be shown. This can also be shown for, and actually this is very easy to show. I mean, this is, yeah. So this is like this some version of like an optimality condition for submodular optimization, right? So because these subgradients or like subdifferentials can be characterized easily, checking this is actually relatively easy, right? And this is the connection of the fact that submodular minimization is somewhat easy to do, right? But in contrast, when you talk about submodular maximization, you can still talk about the same result, right? That x star is a maxima of a submodular function if 0 belongs to the super differential of x, right? But the problem is that even checking this is actually not easy, right? But it turns out that we can actually kind of obtain an approximation, right? So one simple idea, right? So this implies a simple idea, right? Is that if you have an approximation x hat such that 0 belongs to, an outer approximation of x hat, right? Then can we say something about that, right? So it turns out that some of these outer approximations are exactly like local optima, like to the so basically if you take like just the first order like outer approximation, right, where you just take the sets y which are at most a one Hamming distance from x, you'll get a local maxima, right? And then you can get a second order local maxima, third order local maxima, right? So it turns out that these local maxima of submodular functions, from a maximization perspective, give certain approximation guarantees, and we'll actually study this when we talk about approximation algorithm, right? So that's kind of a nice connection here, that you can come up with these approximate optimality conditions, right? And these approximate optimality conditions have kind of these theoretical results that you can show with respect to these polyhedra, right? So yeah, this is kind of a diversion, but just wanted to give you the higher picture here, the bigger picture here. Sorry, so this is the definition of the subgradients, right? And the super gradient. Sorry, and this is a specific example of a super gradient where you compute this super gradient in a specific way. In fact, it turns out that you can compute 3 of these. I'm not going to talk about this right now, but you can compute 3 of these, and you can then extend this to actually compute a family of super differentials, or actually inner bound of the super differential using combinations of these. Okay, so yeah, this is the second super differential, which we call shrink, and you have also a third super differential. Okay, but we'll just skip. Like I think it's just important to understand that you can compute these super differentials, and we'll see. We'll actually come up with algorithms now that use these super differentials in minimization. All right. So in convexity, so there's one more term I wanted to kind of introduce, in the class, is kind of understanding properties of submodular function, right? So there is this quantity called, so you have parameters like strong convexity, Lipschitz continuity, Lipschitz continuous gradients, Lipschitz smoothness, etc., right? The question is that, are there similar characterizations for submodular functions? So there is one specific characterization which actually turns out to give certain improved bounds, and that's the characterization of curvature, right? So the curvature of a submodular function is essentially how close to a linear function this function is, right? And it turns out that this curvature gives actually improved bounds in multiple settings. And the curvature of this function f is 1 minus minimum of j of fj given v minus j divided by f of j, right? And we will actually use this curvature in characterizing certain approximation bounds. Yes, Professor.
Put the previous slide.
Yeah.
The set that is used here is the entire set V only, not some other set that contains J and remove J.
Yeah, that's a good point actually. So we can actually extend now the curvature to compute this on any set X, right? And you can write this as 1 minus minimum of J in X of f of J given X minus J of f of J, right? So this is actually a kind of more powerful notion of curvature, and many of the algorithms actually use this more powerful notion. But for simplicity, just to get a number, we can compute this. But oftentimes the problem with this is that the function gets curved completely towards the end, right? So this curvature actually is equal to 1 if f of j minus v minus j is equal to 0. So if the function gets completely curved like matroid rank functions, then this becomes 0. So that's why a more interesting property is actually this. And this will be useful to us because some of the algorithms have an approximation guarantee that depends on the curvature of f at x star, which is the optimal set, right? And x star could be much smaller than v. So you're right. This is a great point you raised, Professor. So we'll talk about this actually soon when we talk about the algorithms. Right. Are there any other questions? Sorry. Yes, Krishna.
My only question is like if it's min j in x and min j in x, right? So as long as the function is submodular, uh, won't we get the minimum at x equals v?
No. So this is for a fixed set x. So this minimum is for j within x. It's not a minimum over x.
True, but ideally, right? If we want to vary the x, we'll get the minimum at when x equals v, right?
Yes, that's right.
Okay. So,
Yeah. So basically, kappa f of x is greater than or equal to kappa f of v. Right?
yeah. So, are there any criteria where we...
Actually, less than, sorry. Wait. Less than. This is less than this.
Yeah.
So this term can be 1, but this term may not be 1. This will be less than 1. So that's why this becomes interesting. When it's 1, it's fully curved, right? So the interesting case is when it's not fully curved.
So, like, are there any criteria in choosing this x? Like, what x we plan to work on?
Oh yeah. So you'll see this actually right now. It's a little bit vague, but the approximation bound will involve, for example, the curvature of f at x star, where x star is the optimal set,
Okay.
right? So some of the guarantees will involve, the approximation guarantee will involve this quantity, like say 1 minus this quantity, right?
Okay, got it.
And we'll actually take a look at these approximation bounds soon.
Okay, sure. Thank you.
Right? Any other questions? Okay. All right. So now we will start looking at algorithms slowly, right? So minimization of f is kind of natural in settings where you want to minimize cooperation and complexity, where you want to induce cooperation and complexity, and in maximization is where you want to do things like coverage, diversity, representation. So over here also there is like query relevance as one more thing, because you can define f of x given q as the conditional gain, right? And if you want to minimize x here, we are kind of trying to find a set x which is very similar to q. So this problem is actually called a submodular span. It's kind of related to these mutual information things we spoke about, because it's a conditional mutual information. But we want to compute f of x given q, and q here is a query set. So you want to obtain a set x which is diverse yet similar to a query set, right? So for example, you could look at an application where you want, so an application of simultaneously minimizing f while maximizing g is, imagine that you want to maximize diversity, right? Such that you have like query relevance, which is f of x given q as less than or equal to epsilon, right? So you can control this using this kind of query relevance idea over here. And this is another way of formulating the problem. Okay. Okay. So there are actually several applications. I won't go over them. There's data summarization, sensor placement, data subset selection. I'll talk about some of these applications in the next lecture, where we'll actually kind of study some of this more concretely from an application perspective. Then there's cooperative matching for image segmentation, or sorry, basically image correspondence, image segmentation. There's actually like query-driven summarization applications, kind of targeted subset selection applications. Then there is applications like, kind of limited vocabulary speech selection, sensor placement, feature selection. Many of these applications involve submodularity, right? And there are different variants of submodular min, max, and joint optimization. So broadly speaking, this is the class of optimization problems. There are many more, but this is the class we'll focus on, in this, in kind of in this class, right? So in this class, we'll focus on these 4 kinds of optimization. In this lecture, I'll talk about mainly submodular minimization, maximization. We'll see how far we can get. But if not, in the next class, I will complete, I'll kind of finish this off wherever we leave it at today. And then I will look at also difference of submodular optimization and submodular optimization under constraints. Okay. And with that, we'll actually wrap up the optimization part. And then in the next lecture, most probably, we'll talk about applications, right? So this is going to be the plan for the next few lectures. Submodular minimization is where I'm minimizing a submodular function subject to some constraints. Submodular maximization is where I'm maximizing function subject to constraints. And DS optimization, or difference of submodular optimization, is where I'm doing this as a difference of submodular functions. And the submodular constraints version is, for example, this one, right, where you are trying to maximize a submodular function subject to a constraint with another submodular function. So this is minimizing f of x such that g of x is greater than or equal to c, or maximizing g of x such that f of x is less than or equal to b. Okay, so I think with this part, we are ready to now start the algorithms for submodular minimization. But let us actually take a quick break. So we'll take a 5-minute break, and then we'll start off with the minimization part. Okay, but before taking a break, are there any quick questions? Okay, so let us just start in maybe 4 minutes. So we start at 1:40. So it's 1:36 now. We start at 1:40. Yeah. Okay, hey guys. Should we start back? Okay, can you guys hear me?
Yes, Professor.
Okay. All right. So the first problem we'll start with is minimization of f of s, right? So um, it turns out that there are several applications of this. For example, clustering, right? You kind of want to select a clustering of points which are like similar, right? Then what minimization of f of s will do is it will try to get similar groups of points together. So imagine you're trying to group, kind of just separate it into s and v minus s right now, right? So you can solve minimization of s subject to v of f of s and then obtain a set s. So s will be similar and then the kind of rest of the points will be in v minus s, right? And then you can kind of keep doing it iteratively. So you can take v minus s then and then separate v minus s into clusters and so on. So I think this algorithm is called um, this is so actually, sorry, I think, excuse me. So what you want to do is you want to minimize f of s plus f of v minus s, right? So that way you are getting a subset s where basically points in s are as close to each other as possible and points in v minus s are as close to each other as possible, right? And then you can recursively keep clustering points within s and within v minus s once you obtain these two. So this function, the resulting function, actually is called a symmetric submodular function because if you define g of s, so kind of irrespective of what f is, g of s is equal to f of s plus f of v minus s is a symmetric submodular function. And you can repeatedly do this to achieve a clustering algorithm. So this is an interesting application of submodularity. Another application is map inference in graphical models. So those of you who know graphical models, have done a course in it, you must have seen this kind of easing model structure, right? Which kind of comes up in these conditional random fields kind of models. And here the inference problems involves actually a submodular minimization. And so on and so forth, right? So you have multiple of these applications. You have structured sparsity regularization. So we saw this briefly last time that using a Lovasz extension, you can actually induce norms, which is like the Lovasz extension of the absolute value of x, right? This is a norm, and this induces interesting regularization. So this is another application of submodular minimization. So all of these are natural applications of machine learning, and it's important. So the question is, how do you solve this, right? All right. So we're going to start with this family of algorithms for unconstrained submodular minimization. So the reason is unconstrained is because there is absolutely no constraint on A, right? We just want to minimize f of A everywhere, right? So this can be done using several techniques. We are going to talk about a few of them today. So there are actually combinatorial algorithms for doing this. These are actually, I think if I were to go into this, it would probably take me an hour in just covering one algorithm, right? Because these are quite complicated. These are actually related, I believe, to some of the things Professor Chandrasekharan talks about. So I don't know, Professor Chandrasekharan, if you actually cover this flavor of algorithms for some optimization.
No,
But
I
I
don't
think
get that far.
you probably cover the matching style.
I come up to matroid intersection, and beyond that, I don't have time.
Right. So, but I think if you take his course, lot of the algorithms used here are in a similar flavor. In fact, they use a lot of these matching ideas, and they use some nice properties of submodular functions to enable this. But one of the first work which gave a fully polynomial time algorithm it was this work by Iwata, Fujishige, Fleischer, and Schreiber. In fact, most of these are actually big names, in the kind of CS theory and the math community, and they all came together and came up with this algorithm in 2001 and Schreiber in 2000, which won the Fulkerson Prize, right? And this was one of the first to show that you can actually give a strongly polynomial time algorithm. The reason is what I mean by strongly polynomial is that it is independent of the value of the submodular function. Right? So it just depends on the dimensionality. That's it. Many of the other algorithms depend on, like for example, M. Here in this case, you have like M, right? So this M actually is the kind of singleton value, right? So max singleton value. So it kind of depends on the value of this max singleton thing, and that's why it is not really strongly polynomial. This is called so I think this is called like weakly polynomial, and then if it depends on M directly, it's called pseudo polynomial. Yes, professor.
Is there any research that takes one submodular function with one value of M, converts it to another submodular function with a smaller value of M, and says the answers are the same? We have such things in other areas.
Yeah, that's a good point. I have not seen this. I've not seen this work. I think from what I
for example, Eva Tardosh's original work on min-cost flow changes the problem by changing the objective function and saying the same solution somehow operates.
Oh, I see. Yes. Yeah, that's a good point. I think there might be. I'm not aware of it actually. So I mean, apologies for that. I don't know. I think there might be. It sounds familiar. We might have to dig up one of these papers in more detail to see. I do know that some of these papers have this log m dependency, right? So they might be doing something like that internally. But it's a good point. I think it's a good question. Which
I think my memory is playing tricks with me. I thought Iwata was the first guy who cracked this problem, and then the others joined afterwards.
Yes. So I think that Iwata. No, I think these are the first papers actually. I do know that Iwata did give
maybe these are the printed dates, but Iwata might have had a preprint much earlier. That's what my somehow feeling is.
That's possible. Yeah, that's possible. And the other thing worth mentioning is that Iwata also is kind of gave this kind of first weakly polynomial algorithm, which is like the state of the art because it only depends on log m. And for a long time, this was the best, which was like n raised to 4 plus n raised to 5 log n, right? And this algorithm by Orlin in 2009 was the best strongly polynomial time algorithm. But actually, this slides are slightly out of date. So very recently, in 2016 to 2019, there's been work by Yin Tatley and several other collaborators. They have a 2015 or 16 paper in Stocks or Soda, I can't remember, one of those, where they actually give much faster algorithm. So I think the state of the art today is probably n cubed to n raised to 4 for strongly polynomial time. And weakly polynomial time, they've actually got the algorithm to almost n square now. So basically, this is kind of continuously evolving, right? But the whole point is that the community is trying to push hard to try to bring this dependency on n as low as possible, right? But the point is that it is still quite highly polynomial, and to really achieve scalability in machine learning for large-scale data sets, you really require low polynomial time, right? So there is a lot of impact with possible work in submodular minimization, could have a lot of impact in many of these applications in machine learning.
Is the complexity lower for symmetric ones?
Yes. So symmetric ones, for example, there is this pendant pen, the algorithm by what's his name? Kuran algorithm. So he has an order n cube algorithm for symmetric submodular functions.
Okay.
Yeah. So and also I think some of these papers, right, have special cases with symmetric submodular functions where in each of these cases they are able to improve, I think, even the n cube. I'll need to double check on that, but I have a feeling that even the n cube has been improved in the symmetric case. But okay, so the main point is that submodular function minimization is polynomial time solvable, right? So I'll talk about two particular techniques here. So the first technique is this strategy called the minimum norm point algorithm. And this one actually comes from this nice relationship in by Fujishiki, right, and several others, where you have this kind of relationship between dual problem of submodular minimization. Right? So I'll talk about this a little bit first, but before that, let's introduce the notion of a base polytope. Right, so a base polytope is this this polytope, right, which basically corresponds to an intersection of the submodular function along with the constraint. So you have a submodular polyhedron, right? So if you intersect it with the set of x such that x of v is equal to f of v, right? So this is the base polytope. Okay. So unlike the polyhedron, the submodular polyhedron, this is actually a polytope. So in the sense that it is actually a closed, basically polyhedron, right? So it has all of the extreme points, and it's kind of intersecting now with this constraint, which is x of v equal to f of v. Okay. So basically the result is that you can take a regularized problem, which is minimum of x, f of x plus half x square, and you can then compute the dual of this, right? And the dual of this, because this term in turn is like minimum of y in p raised to f of y transpose x, then you can kind of compute the dual of this. Oh, sorry, this is actually max, right? And you can show that the dual actually is this minimum norm point problem, where you want to find the minimum norm point of argmin of u in bf of half u square, right? And once you get this u star, you can actually obtain this set a star as follows, right? So you take the I such that u star of I is less than or equal to 0, right? And basically this a star, but once you solve the dual problem, this a star exactly minimizes f of a. Okay. So if there is an algorithm that can efficiently solve this minimum norm point problem, right, which is to get u star equal to argmin u in bf of half u square, half norm of u square, then you can actually obtain a resulting a star from this u star, right? So it turns out that it is actually possible to solve the minimum norm point problem. So if you want to do this, then can this be done? Well, it turns out it can, and the way we can do this is by using actually the Frank-Wolf algorithm. So for those of you who recall the Frank-Wolf algorithm, right? The Frank-Wolf algorithm is similar to so this is like the conditional gradient descent, right? So the conditional gradient descent is something we studied in I think lecture 4 or lecture 5, where you can actually take a constraint problem, take a convex optimization, and as long as a linear optimization over the polyhedron can be solved efficiently, we can use the Frank-Wolf or the conditional gradient descent, right? So that's exactly the point. Because a linear optimization over P of f, right? So because a linear optimization over P of f, which is exactly the same as a linear optimization over V of f, can be done efficiently, we can actually do this using a Frank-Wolf algorithm, right? So that's how a lot of the continuous optimization actually plays in over here, because a lot of that machinery can be used back. Okay. So it turns out that empirically, the minimum norm point algorithm actually scales much faster. But very recently, there's been some work that has shown that we can actually the minimum norm point algorithm is also can be shown in polynomial time. So this algorithm, right, we can actually give a bound on the complexity of this algorithm, the Frank-Wolf algorithm, right? And in fact, this will use the complexity analysis of the known complexity analysis of Frank-Wolf, right? So anyway, this is on the minimum norm point algorithm. Before going there, I promised you that I'll talk about this this setting, right? So we spoke about the minimization. Okay, so minimization of f using the Lovasz extension, right? So we saw that we can first minimize. So essentially we kind of compute the Lovasz extension, right? And then we minimize x belonging to 0, 1 raised to n of f tilde x, right? And we obtain this as x star. And then second step is to round x star, right? So I think Harsha, you had a question that for Lovasz extension we need x. So basically what I'm trying to say over here is that we want to have an algorithm that does step 1, right, which is minimize x in 0, 1 raised to n of f tilde x, right? So to do this I need to compute the Lovasz extension. Fortunately the Lovasz extension can be computed in polynomial time, right? And using this computation I can now solve this using something like, say, projected gradient descent, right, to obtain a 1 over epsilon square approximation. So essentially we can achieve x tilde, right? So maybe I'll call this x tilde actually. So we can achieve now a x tilde, right, such that f of x tilde minus f of x star is less than or equal to epsilon, right? So once we have this x tilde, the question is, can we now round this x tilde in a meaningful way, right? So is there any questions on the first part? Harsha, does that answer your question?
I think so. I mean, my question was for computing the Lovasz extension, we needed x, right? Or is
Yes.
it we use the complete space of x?
No. So we need an x, right? But the idea is as follows: that this is an iterative algorithm, right? So recall that the subgradient of the Lovasz extension, right? So I'm abusing notation. It's not actually a gradient, but a subgradient of the Lovasz extension at x is nothing but this h sigma x, right? So I just compute the ordering of this, and then I get the subgradient, right? So this quantity now can be computed easily, right? Once I compute this quantity, then I just need to do a gradient descent on this. So I just need to do xt plus 1 is xt minus alpha times h sigma xt.
So we start with some random x initially.
Yeah, so we just exactly. So we just start with some x and then we do the project gradient descent on this, right? So initialize x0 somehow, right? So that's the idea, right? So now the question is, how do we round? Okay, so again, we can kind of use this nice property of the Lovasz extension, right? That once you get your x tilde, right, this quantity is nothing but sorry. So this quantity is nothing but x tilde multiplied by h sigma x tilde. Right? So actually, I'm running out of battery, unfortunately, with my iPad. So it might go off soon. So we'll see. But anyways, I think it'll probably go on at least for the next 10 minutes or so. So I'll try to at least complete this part till then. So we have x tilde multiplied by this part, right? This part, if you recall, is nothing but f of si minus f of si minus 1, right? Where you have the chain of sets, right? So basically what this means is that we can write now this Lovasz extension as a sum of I from 1 to n of some x, maybe I'll just call this, so actually it's some function, it's some constant, right? Alpha x multiplied by f of si, right? And it turns out that each of these are actually greater than or equal to 0. So essentially the Lovasz extension, once you compute this chain of sets, this chain of sets depends on x. Depending on x, once you compute this chain of sets, right, the Lovasz extension is nothing but a convex combination, is nothing but a combination of these chain of sets, right? So now this fact can be, so in fact it's also a convex combination, because you also have that the sum of I, so maybe I'll write this as alpha I. So you also have that it turns out that the sum of I from 1 to n alpha I is equal to 1, right? So because of this property, what you can show is that there exists at least one set Si, right, such that f of Si is less than equal to f tilde of x hat. Can someone tell me why this is the case? Any ideas why? Think about a proof from contradiction, right? So what if f of Si is strictly greater than, so suppose f of Si is strictly greater than f tilde of x hat for all I, right? Now we know that we have this property. So what does this mean? Anyone? So this means that, yeah, exactly, right? So this means that f hat of x tilde is actually strictly now greater than this average quantity, right, which is sum over I from 1 to n alpha I of f of Si, which is strictly greater than now f tilde x hat, which is a contradiction, right? Because f tilde x hat cannot be strictly greater than f tilde x hat. So I mean that there has to be one value in this chain of sets which is less than this. But because this is the minimum of a continuous problem, which is lower than a minimum of a discrete problem, it turns out that actually all of these sets in the chain of sets will be the same. So either the x hat that we get will be a discrete set, in which case we are done, or if it is not a discrete set, we can consider any of the sets in the chain of sets, right? And that will have a value exactly equal to f hat tilde. So this is because of submodularity. Again, I've given a hand wavy proof here, but you can actually make this more concrete, right? So this means that the rounding procedure is very simple. I take my x hat, I form the chain of sets corresponding to s hat, right? Corresponding to x hat, right? And any one of these sets in the chain of sets will be my discrete solution. Is this clear? Yes, Nathan. I can't hear you.
Oh, I wasn't speaking. I didn't hear you. Can you hear me?
Yes, yes.
Okay. Yeah. So, do we know which? So, if we form these chain of sets, we know which one to select if it's less than or equal to our computed value for x hat. Is that how we select it, or?
No, so we select the chain of sets. We select the chain of sets by sorting, right? So this is how we did the Lovasz extension, if you recall. So we take x hat, we form a permutation corresponding to x hat, which is sigma x hat, and this permutation induces the chain of sets, right? And the claim is that any of the sets in this chain of sets will be the solution, basically.
Right. And my my question then is, if you, how do you know which of those sets is the one to choose based off of your computed value for x hat?
You just take any one of them, and that will be the solution, because all of them will be equal. So okay, so like one way is to just evaluate all of them, right, and take the minimum, right? And this claims that there exists at least one set such that this is the minimum, right? But I'm arguing that you cannot have something which is strictly less than, because this is the solution of this continuous optimization problem. So the continuous of the the solution of the continuous optimization problem must be lesser than the solution of the discrete optimization problem, right? So because it cannot be the case that one is strictly less than this. At most it can be equal. It can't be strictly less, right? So because that's the case, and because we have this chain of, we have this result, picking anyone would suffice, right? But I mean, to be kind of clear, to just be sure, you can pick the like have an algorithm where you pick the minimum amongst them, right? And that will work. Is this clear?
No, I'm not. I'm not understanding it.
Okay. So you have your set x hat. You have your point x hat, right? And now corresponding to x hat, you have your chain of sets S0, S1 until S of n. Some of these may be equal also, right? So you have some chain of sets, right? Now the claim is for all I from 1 to n, right? F of Si will be equal to F tilde of x hat. So you pick any one of them, they will be the solution. Is this clear?
Is x hat the solution that you get from doing this projected gradient descent?
Yes, exactly. Exactly. Okay, so there is one caveat. Okay, good. There is one caveat. So all of this assumes that x hat, f hat of x hat, right? All of this so far assumes that f hat of x hat is the exact minimum. Okay. So in practice, okay, good. So actually, I kind of forgotten about this part. So what if PGD, the output of PGD, gives an epsilon approximate solution, right? So that means that we obtain an x hat such that f of x hat minus f of x star is actually less than equal to epsilon, right? Then what we do is that then the claim is that you can do that the minimum amongst these, right? So minimum from I from 1 to n, if you take the minimum of these minus f of x star, right, this will be less than equal to epsilon. Okay, so all of this is assume x hat is exact minima. But if x hat is not the exact minima and we have an epsilon approximate solution, then what we should do is take the minimum amongst these chain of sets in terms of the function value. Is this clear now?
I'd have to look at this later. I'm not getting it. My confusion is this chain of sets, right? If I mean, is S0 like containing one element, S1 containing the first two, and then so on and so forth? So if any one of them works, then like, what's the actual solution then? Because you could just pick a vector that has all of them.
No, S is a chain of sets, right? So I'm saying one of these sets. So first of all, right? So the chain of sets is induced by the permutation sigma x hat. Okay, so there's a permutation. Right, so there's a permutation based on x hat. So okay, so now consider that x hat is exactly a discrete solution, right? So if x hat comes out to be one of the vertices of the hypercube, then there is exactly one S that will correspond to the chain of sets. Okay, because there are multiple possible permutations, but if you write down the chain of sets that come in this way, so okay, so actually maybe imagine that you have a chain of sets now that are induced by this ordering that look like this, right? So now if x hat is looks like if x hat is completely discrete, then there is just one one set that corresponds, right? So then there will be just be one solution. Now imagine that, so take this as case 1. Imagine case 2 as being 0, 0, 0 0.5, 0 0.5, 1, 1, right? So now, based on this, we can actually induce some orderings, right? So you have these two being the same, then you have these two, right? And then you have these two, right? So essentially your chain of sets now is going to be, so say, so maybe I'll just kind of order this a little bit differently. So say the second case is where you have 0.51, 0.5001, right? So now I order this, right? So if I order this, I start with, say actually my ordering, I start with the largest one, right? So I start with the largest one, and then I have this, right? So basically I have S0 equal to 2, 3, right? Sorry, 2, 5, okay? And then I have S1, which corresponds to 1, 2, 3, 5, right? And I have S2 that corresponds to everything, 1, 2, 3, 4, 5, 6. Okay. So can you see why you have now 3 distinct sets in this case over here? Because the breakpoints that are there, right? The breakpoints are coming up at either 0, 1, or 0. 0, 0.5, or 1. There are only 3 breakpoints, right? So that's why when you take this chain of sets, you will just have these 3 chain of sets.
Professor, in X hat case 2, the second and the sixth element are 1. So wouldn't S0 be 2, 6?
Oh, sorry, I think I wrote this as 5 by mistake. Sorry, I think it's 6. Yeah, okay. So this is 2, 6. Then this is 1, 2, 3, and 6. Right, and this is 1, 2, 3, 4, 5, 6. Yeah. So what is the question here? So, so are you saying that 2 and 6 should be different sets? No, 2 and 6 won't be different sets, because the permutation is kind of, so the chain of sets here are depending on where the breakpoints are. That's the critical thing. Okay, the permutation is looking at where the breakpoints are, and it is merging these together. So it's not that 2 and 6 will be 2 different sets. That's wrong. The set will be 2, 6. Does it make sense? So Nathan, does that answer your question?
I'm sorry. I have to look at this later. I won't spend any more time on it if you don't want to. I'm not getting it. I have to look at the slides again.
Okay. I mean, I can repeat it. There's no issue with that. I can repeat it. Okay. So like, what part are you not understanding in this exactly?
I suppose I don't understand this like chaining of sets like this. I don't get how that's formed. I don't know. Yeah.
So okay, so at a high level, maybe so the problem is that I'll have to go ahead and derive everything, right, to see exactly what's going on, but to kind of show what's going on. But I think at this point, maybe you can just believe me, right, that the chain of sets is formed at where the breakpoints are. So can you see that the breakpoints over here? Okay, so maybe take an example now that the x hat. So unfortunately, I don't have space, but maybe I'll write down over here. So imagine a third case where x hat is actually is like 1, 0.8, 0.7, 0.4, 0.3, and 0.9, right? So over here, everything is distinct, right? Does it make sense? So since everything is distinct, we have a chain of sets where everything, I mean, the entire chain of sets would be like individual points, right? So the chain, so you start with 1, right? So this would be the first element. Then you start with 0.9. So that's so basically you have one subset of 1 comma 6, subset of 1 comma 2 comma 6, right? And so on and so forth, right? So now you have chain of sets that differ with only one element at a time. Okay, but very often the solution that you get from the Lovasz extension would look more like this rather than looking more like this, right? So that's the reason why your chain of sets, you have to see where the breakpoints are and then merge everything together in this breakpoint. So the breakpoint here is you have 1, then you have 0.5, and you have 0. Okay, maybe we can take this offline if you have more questions to understand this.
Yes.
Are there other questions on this? What do you mean by different probabilities? So actually my iPad is running out of power, so let me just get the slides. Just give me 1 minute. Sorry. I'm just pulling up the slide because my iPad will run out of power. So I won't to use the pen anymore, but at least we can continue with the class. So actually, I'm not clear what you mean by probabilities. Actually, Jiyashu. I mean, here the x is the solution that you obtain. The x here is the solution that you obtain from the Lovasz extension. So recall, right, that you are minimizing the Lovasz extension between 0 to 1, 0, 1 raised to n, right? And you will get some continuous vector out. So this is the x. Each coordinate of x will be between 0 to 1. So it's not necessarily related to the probabilities. I mean, though you can view it from a probabilistic perspective, which I'm not getting into because that would be, slightly more complicated. Yeah. So actually there is a probabilistic interpretation of this, like this way, right, where you have this sum of this. Oh, sorry, I think. So where you have a sum of this, right, where you have this alpha i's, these alpha i's can be seen as probabilities because they sum up to 1. So you have this interpretation since they sum up to 1, but yeah, okay, maybe you can think about this. If you're still stuck, we can discuss this offline, right? So okay, so I wanted to spend some time on constraint optimization, which is a little bit more advanced, but I'll at least try to get the high level kind of intuition across. So just give me 1 minute. I'll just share. So just. Okay. Okay. All right. Okay. So let's. So unfortunately, we'll have to do it in this way. But you can still see my screen, right?
Yes, Professor.
Yeah. Okay. So we will look at now the constraint problems a little bit, and I'll keep this at a high level. So I just want to kind of give you the main intuitions here of what's going on. We saw unconstrained optimization, right? So here we looked at the Lovasz extension style approach, and we looked at the minimum norm point algorithm, right? And both of these are polynomial time problems, okay? So this is polynomial time. Now, in the case of constraint problems, it turns out that this is actually hard, right? The constraint problems is hard. In fact, it's not optimizable up to any constant factor, right? So actually, let me just try to open this as a PDF. So sorry, just give me 1 minute. Okay. This is slightly better. So all right. So we are interested in constraint problems, right? And yeah. So in general, unfortunately, with constraints, this problem is very hard, right? So it turns out that even with simple constraints like cardinality, lower bound constraints, like something like size of A greater than equal to K, right? This constraint makes this problem very hard. And this is very important. This problem becomes like a balanced cut, which again is kind of like when you're doing this with a graph cut, right? And you want to make sure that your cuts that you achieve in the end are not very small, right? So you don't have trivial cuts. So this problem turns out to be an instance of a balanced cut problem, but balanced cut is actually NP hard, right? And in fact, there are actually lower bounds for this problem, which is polynomial factors, right? So one thing which is important over here is the notion of an approximation guarantee, right? And what I mean by an approximation guarantee is that we are achieving. So imagine that you're solving this problem, right? But you're achieving a set A, which is an approximation of this, right? And this approximation now is up to a factor alpha, right? So in the case of minimization, this alpha is greater than 1. So for example, if I have a 2 approximation, what I mean by 2 approximation is that I'm achieving a set A which is guaranteed to be less than twice the optimal value, right? So imagine that I'm doing a minimization problem, my optimum is at 1, right? Unfortunately, finding 1 is NP hard. I cannot find the value 1, right? So I won't find the set in polynomial time. I won't be able to find a set that gives the value 1, but I can give an algorithm which is guaranteed to find a set which has a value guaranteed to be less than equal to 2, right? So such an algorithm is called a 2 approximation, okay? So in such cases, when problems are NP hard, we resort to approximation guarantees, right? And we want to be able to find kind of algorithms that can give this approximation guarantee in polynomial time. Okay. So this problem naturally generalizes a lot of the network optimization problems that appear in like combinatorial optimization, right? So for example, you have like this these kind of problems that minimize the function over a set of say edges, right? So imagine that here I have S being a set of edges in a graph, and imagine you're trying to find a cut, right? So my cut here is I'm trying to find the minimum cost cut so that I cut these edges and I can separate this basically into two groups of vertices, right? Formed by S and formed by T, right? So this minimum ST cut problem is a cut problem where I'm cutting these edges such that the set of edges once cut forms basically separates the nodes into two groups, right? So that's called a cut. And precisely what we mean by ST cut is a cut such that it separates the two vertices. It separates the vertices into two groups. One group contains S and one group contains T, right? So an application of this is image segmentation, where typically a user draws a foreground, like he draws like few pixels in the foreground and he draws few pixels in the background, right? And I want to find this segmentation of which is like a cut amongst the pixels such that I can divide the foreground into the background, right? Other applications include like matchings, right? So I have like a set of nodes over here and I want to find a set of edges which match the nodes on the left to the nodes on the right? And by definition, a matching means it is one-to-one. So I want one node from the left-hand side being matched to one node on the right-hand side. Similarly, there are paths. So paths means it is a set of edges which join S to a T, right? So this is a ST path. And finally, you have a spanning tree, right? So spanning tree, I'm sure many of you are aware from an algorithms course where you cover a lot of these spanning trees, right? So a lot of these problems can be viewed as minimum weight problems, right? So you're like each of the like edges in the graph has a weight, right? And then you want to do a minimum weighted cut or a minimum weighted matching or minimum weighted ST path, right? But a natural extension here is that imagine you define a submodular function over the set of edges, right, or the set of vertices, and you want to find a minimum ST cut such that it minimizes a submodular function. So this is an image segmentation problem, right? So here you are defining this network and you have like a set of pixels that form a foreground, pixels that form a background, and you want to get this perfect cut, right? So there is this work kind of a few years back where they looked at this notion of cooperative cut and they induced a cooperation over these edges. So what essentially happens with just doing a minimum ST cut is that where you have these elongated edges, right, the minimum ST cut will try to cut this because it's not seeing a gain in having a very elongated cut like this, right? So you can see that if you were to actually do a cut, then it would be super elongated. So there is not as much gain from from what a cut sees if you just pose it as a minimum ST cut. So that's where submodular functions become useful because you can model this kind of interaction over here and you can model this cooperation, right? So you can say that if I have this long edge, then I want to add a discount with this long edge, right? So this then becomes what we call as a cooperative cut. And now this cooperative cut is where we are trying to minimize the submodular function over the edges, right? So it's not a sum of the edge weights, but now it's a submodular function over the edges. Okay. So there are a few approaches that can be used to study this constraint submodular minimization, right? So one is where we can do a convex relaxation, right? And the second strategy is where we can use actually a surrogate function, right? And a surrogate function is like a proxy function, which we will see actually, and this relates to the super gradients that we spoke about, in the beginning. Okay, so this is the approximation algorithm, right? So I have a slide over here. So given a minimization or maximization problem, we want to obtain an exact minimizer. So that implies an approximation factor of 1, right? But if the problems are NP hard, then it's impossible to achieve this exact minimizer in polynomial time, right? So an alpha approximation factor is where I'm achieving this, where I have this alpha such that f of x is less than or equal to alpha times f of x star, right? Where x star is the global minima. And in the case of minimization problem, alpha is greater than 1. So I gave this example of a 2 minimizer, right? So there alpha is equal to 2. You can do the same with maximization, right? Except that there alpha is less than 1 because you're trying to maximize it, right? So you will achieve something that is lesser than the maximum. Okay. So in the case of constraint optimization, there is this nice framework which uses these linear upper bounds everywhere, right? So the idea is that you compute a linear upper bound of a submodular function, and then this linear upper bound is actually modular, right? So you're converting now the submodular function using the supergradients into a modular upper bound, and you are then minimizing the modular upper bound every time. Okay, and this problem actually is easy because it's an easy sum of weights problem, right? So it's exactly a weighted cost minimization problem, which can be done in polynomial time. So you have the minimum ST cut, minimum ST path, minimum perfect matching. All of these problems can be solved in polynomial time, right? Any questions on this so far? Okay, so the intuition here is that we want to compute upper bounds of this submodular function and minimize these upper bounds, right? And we want to minimize these upper bounds iteratively. So the idea is that we are using these proxy functions, these upper bounds as proxy functions, and minimizing these till we come up with the objective value, right? And the goal is that we always want to improve the objective value as this proceeds, right? So this is the idea, and this is what comes out basically, right? So we compute these modular upper bounds, and then we minimize these modular upper bounds using, which is the minimum ST cut, path matching, etc. Okay, so it turns out that this algorithm, which is called majorization minimization, right? So this algorithm has actually bounded approximation factors. So it can achieve a factor that depends on the curvature as follows, right? So it's n over 1 plus n minus 1 multiplied by 1 minus kappa. So roughly speaking, this is 1 over 1 minus kappa, right? But there is also this n kind of factor over here, right? It turns out that there is a much more complicated algorithm called the ellipsoidal approximation, which also achieves a similar factor, but it reduces the n to a factor of square root n, right? But asymptotically, in terms of kappa, both are the same, right? So as long as the function has a bounded curvature, the factors achieved by this is roughly the same, right? But it turns out that this majorization minimization is a much more practical algorithm and is almost 100 times faster compared to the ellipsoidal approximation. Okay, so there's just some concrete approximations for different constraints. I'll probably skip this, right? Okay, so actually with this, we can now move on to submodular maximization, where we look at greedy variants of algorithms. But I think this is probably a good time to probably stop for today's lecture. And I think next time I'll go over maximization in much more detail, right? And then I'll also talk about, some difference of submodular optimization and the submodular constraint problems. So are there any questions on this at all with what we covered today? Unfortunately, my iPad is still not on, so I won't be able to write, but I think at least I'll try to discuss. Yeah. Yes, Nathan.
Yeah, I just want to make sure. Can you upload these marked version of these slides to your GitHub repository?
Yes, I'll do that. Yes.
Okay.
Yeah. Any other questions? Okay. So maybe then probably why don't we kind of end over here today? Go over this in detail. If you are stuck somewhere, feel free, I mean, like either next week office hours or even in the middle of the week, reach out to me and I'll be happy to answer any questions that you guys have. I mean, the main thing is to kind of understand what's going on. It's a little bit at a high level. And I mean, minimization is a little bit more mathematically involved. So That's the reason why I kept the minimization portion much smaller, and I didn't even attempt to go over any of the combinatorial algorithms because it is just much more complicated, right? Hopefully, I think the maximization will be more clear next time, and also probably more useful to most of you when you use submodular optimization, right? Because most of the problems that you'll see machine learning will involve maximization. Okay. All right. So sounds good. Have a nice weekend, guys, and I'll see you next week. Just a reminder, please get started on the projects if you have not, right? And make sure you start putting together set of slides soon within the next 1 or 2 weeks. I will announce a schedule maybe next week, right? Starting on the 23rd. Looks like we have like 12 or 13 students in total. So I will actually kind of group the students into maybe 4 per day or something like that, and have around 45 minutes per student, right? So I'll put together. So again, we'll start on, I believe it's 23rd. So today is 2nd of April, right? So yeah, so it's 23rd. So it's 3 weeks from today. So 23rd will be the first presentation. So I'll like randomly pick 4 of you to go the first week, right? And then randomly pick 4 others to go the second week, and like 4 others to go the last week, right? So I understand that those who are going first have a slight disadvantage. So it's fine if your work is not complete when you're presenting it. Make sure that by the time you submit your final project report, that make sure that it's complete for that time. Yeah. Any other final questions? Okay.
I was just making sure the paper readings are also lumped in with the project presentation.
Yes. So it's going to be roughly 45 minutes, I think, per person, and or maybe 40 minutes, right? And probably you can do like 15 minutes for paper presentation and 25 minutes for the project presentation, right?
So there's 2 papers and 1 project, right? In 45
Yes.
minutes.
Yes.
Okay, thanks.
Yeah. So I mean, I gave you a rough suggestion, right? But I mean, I'll leave it up to you to organize the amount of time you want. I would spend like slightly more time on the project, but I'll kind of leave it up to you to kind of figure out the time balance. Yeah. Okay.
Professor, given that we have more clarity on the projects now, can we change the papers that we put on the Google Sheet?
Yeah, sure, absolutely. Yeah, so if you have, if you want to change your paper now, you can go ahead. Yeah. Just make sure you update the Google Sheet. So I'll create another tab there with a list of students and the timings, right? So we'll like for April 23rd, and I'll try to finalize that by next Friday. And the plan is that I'll probably come up with a homework. Like as I said, it's going to be just 2 questions right now, and the homework I'll put out basically by this weekend, right? So so basically that will give you some exposure on submodularity, like showing how some simple functions are submodular, and it kind of implementing a greedy algorithm. We'll actually cover greedy algorithm in the next lecture, but it will give you a good kind of idea of how to implement some of these algorithms, right? And I think hopefully you will enjoy that. Yeah. Okay. Okay, guys. Sounds good. Take care. See you next week.